Hello, it's Mr. Fraley. We're going to be going over the parts of a problem guided practice. So follow along. This will help you complete that assignment and get the most out of it. If you'll pull up the problem, be sure to put down your period that you're in, which class period, and as you scroll down you'll see a picture of a tree. And it says above it, you can tell the age of a tree by counting its rings. You find a tree that is 60 millimeters thick. Every year, a new ring adds 2 millimeters of thickness. In how many years will the tree be 100 millimeters thick? Okay? So we're not going to be solving for how many years in this guided practice. Doing this will have, solving this kind of problem has 2 steps. The first step is to create an equation that describes, what's happening in the story. And to do that, we need to identify the parts of this problem. Now, every problem has 2 main parts to it. There's the sort of information up front and the question at the end. And it's important to know where one stops and the other picks up. In that starting information, you're going to get a lot of useful details. And I want you to be looking for 4 main details in the problem as a whole. The first one that we need to identify is called the starting amount. Okay? So the starting amount. Now the starting amount is sort of where we are before any changes take place. Okay? So for example, it says, here we're going to ask ourselves, how thick would this tree be if it never grew another ring? So imagine the tree when we first find it. We're scientists, we are studying the tree, we have a little table here, and we mark off the first year, the second year, the third year, the fourth year, so on and so forth, as we study this tree. Okay? But before the first year is over, because we make our first opening measurement, the first year we find that it is 60 millimeters thick. And it's going to grow 2 millimeters every year. So it is changing each year by 2 millimeters. Okay? The starting amount asks us about this number before our first year is over. So in this case, our starting amount would be 60 millimeters. Okay? It's your starting amount. It's not a fraction, I'm just underlining. Next. So here, the starting amount is, this first question, it is the thickness in the beginning of the problem. Think beginning and starting. It's the same idea. The starting amount is where we are at the beginning. Next, we need to identify, we're going to call our rate. So the rate is the degree, is the amount by how much we are changing. Okay? It will either be an increase or a decrease. In this case, ask yourself, by how much is the tree's thickness changing? And as we said earlier, it's changing by 2 millimeters. So 2 millimeters per year is your rate. I want to make something clear. This is a common mistake. But your 2 millimeters, your unit is not, am I writing 22? Let me be clear. 2 millimeters, my units are not millimeters. Okay? Our units are millimeters per year. Okay? think of like the difference between miles and miles per hour. One describes a distance, the other describes a speed. And a speed is another kind of rate. Here we have a thickness, and here we have a rate of our thickness. So it's 2 millimeters each year. Now, yeah, that's the rate at which the tree grows thicker, the first option there. For number 3, we're going to identify the variable. There is no number attached to this part of the equation. It will be represented as a placeholder for a number we are looking for. So these have been numbers so far, but my variable is not going to be a number. It's going to be a letter. It's going to be a letter to stand in for some value that we don't know yet. Remember, the word variable, a variable is a number that can change. It'll be X or Y or V or W. Later on you might see some Greek letters come up, but that's down the road. But for right now, it's just not a number. It's not any number that we know. So we're going to use a letter. Now, the variable is often named in the problem's final question. Okay? Now, although your variable isn't some known number yet, it's always going to represent an idea. Okay? And whenever I assign my variable its identity, so to speak, it's a placeholder. It doesn't change, what it stands for. Okay? So, a good way to identify our variable is to ask yourself, what value is the question of this problem actually asking me about? Okay? So, remember, I talked about it's important to look at the information in the beginning and the question at the end. And here, my question at the end is, in how many years will the tree be 100 millimeters thick? Note, the question is, in how many years? So it's asking you about the years of growth. How many years will it be growing? So the number that it's asking you about is your variable. Okay? In this case, it's going to stand for years, so we'll use the letter Y. Sometimes people will use T for time, but it's still going to stand in for the number of years. And I want you to notice something. Look here. You see millimeters and millimeters, right? Note my unit for rate isn't just millimeters, it's millimeters per year. Another way to identify the variable, if you can find the rate, you've already found the variable. Think millimeters per what? Years, okay? And that will always be the case, even way later in the math. That's years of growth. Hopefully I don't run out of space here. For my last idea, it's what we call the target. Okay? Now we think of a target, we think of bow and arrows, right? Sort of aiming at something. Well, this is the value that we're aiming for, where we want my tree to be. Okay? What thickness do we want our tree to be at? And in the problem, let me read exactly what you'll see. It says, finally identify the target of the equation. This is the number that we are aiming for. In this example, ask yourself, which value describes the situation after some time has passed? And so my target just enough room. My target is, that's right, 100 millimeters. Because that is how thick we want to know. That is the thickness that we are asking about. When will it be this thick? So once we get this information written up, see, kind of all lined up, and I went in this order for a reason. It's the starting amount. The equation we write will be the starting amount plus the rate times the variable equals the target. Okay? Plus times equals. Technically, these two are grouped together. I didn't write a parentheses, but know that these are they're kind of married, right? They're kind of stuck to each other. Okay. So let's write our equation down below. My equation is, you see 60 plus 2 times y equals 100. 60 plus 2 times y, we write 2y, that means 2 times y, equals 100. And that's my equation. Note, earlier in my table, we had 60, and after the first year we had 62, after the second year we had 64, after the third year we had 66, fourth year we had 68. That's 60 plus 2 times 1 for 62, 60 plus 2 times 2 for 64, 60 plus 2 times 3, 60 plus 2 times 4. Okay? We see that that works. So this is my equation. 60 plus 2y equals 100. All right? So that all being said, we're going to look at the next example on the next page. At the end of that one? And we end with the variable, not with the equation. So on the next page, we look at different kinds of rates. Now, up to this point, when we've been working with rates, we've been looking in terms of time, right? Like a kid growing taller, or a tree growing thicker, or money in my bank account. You know, there's been more money in my bank account over time. It's always been increasing over time, okay? But not every rate relates to time. There are other kinds of rates as well. Some common examples. You know, you can pay someone for their work per hour, sure. But you can also, let's say, if you get new carpet in your house, you will likely pay so much money per foot of carpet or per square foot of carpet. Or when you buy ribbon, you'll pay per yard of ribbon. And that's a rate too. As the amount of material goes up, the amount we pay goes up. And that's a rate. So rates are so common, you may see them where you don't realize. Not every algebra problem asks about a change over time. This is the top of the second page. The idea of the rate is a very useful one that you will see in many surprising places. For example, you could say that there is a rate of 25 cents per quarter when counting coins in your pocket. This is a per coin rate rather than a per year rate like our last problem. So here a problem says, Maria has $4 in bills in her pocket, but she needs $7.50 to buy lunch. She has a jar full of quarters that she can use to cover the rest. How many quarters should she take to have exactly $7.50? So she has some money, right? She has some money. She'll like a stack of bills, okay? And she has a jar, right? She has a jar and it's full of coins. Okay? I'm not going to draw all these coins, but you get the idea. Okay? She wants to take some amount of coins, right? Plus some amount of coins so that she goes from $4 to $7.50. Okay? So yeah, we're adding that many coins to give me that much. Okay? So the question is, how many coins does she need? Right? Well, to figure this out, we can set up an equation. Okay? And we're going to do the same things we did before. We have first the starting amount. Let me roll that back. Here. The starting amount we found that. Then we found the rate. Then we found the variable. Then we found the target. Okay. So, looking at this, at the beginning of the problem, before she took any quarters, how much money did she have? That's my starting amount. That's right. She had $4. Okay? Now her rate. Think earlier when we had the years. With every year that we counted, because we're counting by years, for every year that we counted, the tree was 2 millimeters thicker. Now here, the thing that we're taking, instead of adding years, now we're adding quarters. And for every quarter I take, I gain 25 cents. So that's my rate. That's $0.25 per quarter. Remember earlier when my top unit was millimeters and it matched my rate, it matched my starting amount, was that we had millimeters and millimeters. Here we have dollars and dollars. And earlier we had years and years. Now we have quarters, and we can write quarters for variables. And that's my variable is going to be, I'm going to say Q for quarters. Okay? So another thing we can use to find my variable, maybe you can't quite find your rate, and so you want to try to find your variable first. Look at the question. Remember, we said the variable can be found in the question. How many quarters should she take to have exactly $7.50? I'm cutting to that last sentence where the question is, right? We can think of the whole problem as being a question, but really to me a problem is in two parts. That's why we call this assignment parts of a problem. There's two parts. There's the information at the beginning that describes a story, and then a question about what happened, right? Or what might happen, or what will happen. But it is a question, right? So the question is, how many quarters, right? So, how many quarters would she have to take? And that's my variable. I don't know that number yet. In the last one, we didn't know how many years it would take. And here, we don't know how many quarters it will take. We're not finding that value today, but we're learning how to set up the equation, because that's an important first step. And lastly, we need the target, and that is where she wants to be at the end after she's finished taking the quarters. In this case, we express our target as, how much does she want for her lunch? $7.50. So we're going to write that, $7.50. It's just like earlier, starting amount plus the rate times the variable equals the target. Starting amount, that's 4 plus, remember, write 0.25. Otherwise, you're adding $25. You be sure you're showing 25 cents with that decimal. 25 cents times the number of quarters. So 1/4 is 25, 2/4 is 50, 3/4 is 75. That's 25 times 3, right? A 4th quarter gives me $1. So that's times 4. So it's the rate times the variable. Remember, keep the idea of a rate and a variable separate. They are two different ideas. And then that's going to equal my target value, which in this case is 7.50. So, and that is my equation. 4 plus 25 hundredths times Q equals 7.50. Or $4 plus 25 cents times the quarters equals $7.50. Okay? And you can write it like that. Okay? Like that. I have to look at the screen to know where I'm pointing. Alright? I want to say that's the end. Yes, this is the answer to the first question, second question, third question, fourth question, the last question. Okay. And that's it for this assignment. Thank you for watching. You have a great day.